When the power grid fails and supply chains collapse, that drawer full of dead electronics suddenly becomes more valuable than gold. Today, we're exploring how to transform broken gadgets into functioning survival tools using nothing but basic knowledge and a bit of percussive maintenance. Old technology doesn't become useless just because it's obsolete. Inside every discarded device lies a treasure trove of components: motors that can move air or water, batteries that can be coaxed back to life, screens that can become light sources, and circuits that form the building blocks of essential tools. While everyone else is fighting over the last canned goods, you'll be building functional equipment from what they've left behind. This isn't about nostalgia. It's about understanding that a $20 broken fan contains the same fundamental technology as a $200 new one. The difference is just packaging and planned obsolescence. So let's get started with the basics of electronic salvage. First, let's talk about what to look for when cracking open old devices. Not all electronic waste is created equal. Batteries are your primary target. Laptop batteries, phone batteries, even old camera batteries can often be restored or repurposed. Look for lithium-ion cells, usually cylindrical or rectangular pouches. Even if the device won't charge, individual cells inside the battery pack might still be functional. Motors are everywhere. Computer fans, DVD drive mechanisms, old electric toothbrushes, kids' toys. Any motor that spins can move air, pump water, or generate electricity when turned manually. The small, brushless fans from computers are particularly useful because they run efficiently on low voltage. Wires and switches seem obvious, but quality matters. Look for stranded copper wire rather than aluminum. Switches from mice, keyboards, and game controllers are usually rated for thousands of presses. Circuit boards themselves contain resistors, capacitors, and LEDs that can be disoldered and reused. Broken screens, whether from phones, tablets, or laptops, contain LEDs along the edges for backlighting. These can be harvested and repurposed. Even shattered LCD panels can become light diffusers or indicators when backlit. The key is thinking in terms of function, not form. That dead laptop isn't a laptop anymore. It's a power supply. 3 fans, a battery pack, switches, a screen full of LEDs, motors from the disk drive, and meters of useful wire. Let's start with batteries, because power is survival. Here's how to test and potentially restore cells that others have given up on. First, you need a multimeter. If you don't have one, find one. They're in every garage and toolbox in any abandoned area. Set it to measure DC voltage. For lithium-ion cells, a healthy cell reads between 3.7 and 4.2 volts. Anything above 3 volts might be salvageable. Below 2.5 volts, and you're looking at a dead cell. But here's the thing. Battery packs often fail because one cell dies while others remain functional. Open the pack, test each cell individually, and you might find 3 good cells out of 4. To restore a depleted cell, you need a slow trickle charge. If you have any working power source, even a small solar panel, connect it through a resistor to limit current. A 100 ohm resistor works for most small cells. Charge slowly over several hours, checking voltage regularly. Never charge a battery that's hot, swollen, or damaged. Lithium fires are not your friend. Once restored, these cells can power LED lights for days. Run small motors, or charge other devices through simple circuits we'll build later. Store them properly, keep terminals from shorting, and they'll serve you far longer than you'd expect. Ventilation can mean the difference between a livable shelter and a suffocating box. Here's how to turn any salvaged fan into a portable cooling or ventilation device. Most computer fans run on 12 volts, but they'll spin on much less. You can power them with as few as 3 or 4 volts. They just run slower. Connect your restored battery cells in series to reach the needed voltage. For a 12-volt fan, 3 lithium cells in series gives you 11.1 volts. Close enough. The wiring is simple. Fans have 2 wires. Red is positive, black is ground. Strip the ends, twist them to your battery terminals, and the fan spins. Add a switch salvaged from any device for control. That's it. No complicated electronics required. For ventilation, mount the fan in a window frame or wall opening using whatever materials you have. The direction matters. Orient it to pull hot air out rather than push cold air in. Hot air rises, so mount exhaust fans high. Here's where percussive maintenance comes in. Sometimes an old fan just won't start. The bearings are sticky or internal contacts are corroded. Give it a firm tap on the side. Not a destructive smash, just a sharp knock. The vibration can free stuck components. Tap it again. Still nothing. One more firm rap, and there it goes, spinning smoothly as if it never stopped. Broken screens become makeshift light sources and indicators with surprisingly little effort. Phone and tablet screens have LED strips or arrays along the edges for backlighting. Carefully separate the screen layers. You're looking for either a strip of white LEDs or a light guide connected to LEDs at the edges. These typically run on 3 to 5 volts. Connect your battery to these LED strips, and you have an emergency light source that draws minimal power. A single small lithium cell can run a phone's backlight strip for 20 to 30 hours continuously. For indicator lights, harvest individual LEDs from any circuit board. They're the small colored domes soldered to the board. Heat the connections with a lighter or hot metal, and they lift right off. Remember, LEDs have polarity. The longer leg is positive, connect them backwards, and they simply won't light. No damage, just flip them around. Add a resistor in series with any LED, usually something between 200 and 1000 ohms, depending on your voltage source. This prevents burning them out. The resistors are the small cylindrical components on circuit boards, usually marked with colored bands. These lights can mark trails, signal others, or simply provide enough light to navigate a dark space without wasting battery on bright flashlights. Now let's combine components into functional tools. We'll build a battery tester and a continuity checker, both essential for further salvage work. For a battery tester, you need an LED, a resistor around 470 ohms, and 2 wire probes. Connect one probe to the LED's positive leg, connect the resistor to the negative leg, and connect the resistor's other end to the second probe. Touch the probes to any battery. If the LED lights brightly, the battery is good. Dim light means weak. No light means dead or backwards. Simple, effective, and requires no meters. A continuity checker works the same way, but tests if wires and connections are intact. Same circuit, but you're touching the probes to the 2 ends of a wire or circuit path. LED lights up, the connection is good. No light, something's broken or disconnected. Here's a useful tool, requiring a motor, a hand crank generator. Take any small motor. When you spin the shaft manually, it generates voltage. Connect it to your battery through a diode, which prevents the battery from spinning the motor backwards. The diode is a small component with a line on one end found on any circuit board. Current flows from the unmarked end to the marked end only. Now when you crank the motor shaft, you're charging the battery. It's not fast, but it works. 10 minutes of cranking might give you an hour of LED light. Sometimes these motors are stubborn. The shaft won't turn smoothly, or it feels stuck. A quick smack on the motor housing often frees internal brushes or clears dust from the bearings. Give it a tap, try again, another firm knock, and suddenly it's spinning freely, generating power with each turn. Let's demystify a few concepts, because understanding beats memorization. Voltage is pressure. It's how hard electricity pushes. Batteries provide voltage. More voltage means more push, like higher water pressure. Current is flow. It's how much electricity moves through a circuit, measured in amps. More current means more power consumption, like wider pipes flowing more water. Resistance is opposition. Components resist current flow. That's often useful because it limits current, preventing damage. Measured in ohms, here's the relationship. Voltage equals current times resistance. V equals I times R increase resistance. Current decreases, increase voltage. Current increases. This is why we use resistors with LEDs. Without them, too much current flows, and the LED burns out instantly. Series and parallel are the 2 ways to connect components. Series means one after another, like train cars. Voltages add, but current stays the same. Connect batteries in series for higher voltage. Like parallel means side by side, like parallel parking. Voltage stays the same, but current capacity adds. Connect batteries in parallel for longer runtime. That's it. Everything else is just combinations and applications of these principles. Before we wrap up, let's address the elephant in the room. Yes, a concerning amount of this tutorial has involved hitting things. There's actually some science here. Corrosion creates poor connections, and vibration can temporarily improve contact. Cold solder joints, crack, and physical shock can momentarily close the gaps. It's not a permanent fix, but in survival scenarios, temporary is often enough. So here's your final takeaway. Save every piece of electronic waste you find. That broken laptop is a hardware store. That dead phone is a toolbox. And when in doubt, give it a tap. That's it for today's tutorial. Now go forth and salvage responsibly. Or at least entertainingly.